This table basically summarizes the form of indefinite integrals for many of the functions we have studied so far, and the substitution method helps us use the table to evaluate more complicated functions involving these basic ones. So in this section, we combine the substitution rules which we studied in chapter 5 with algebraic methods and trigonometric identities to help us use this table, and sometimes we have to rewrite an integral to match it to a standard form which is given in the table. So here is an example. Compute the square to evaluate the integral. This is basically an indefinite integral because no limits are given. Now, taking 8x minus x square. Taking minus sign common, we get x square minus 8x. Completing the square, I get this form, 16 minus x minus 4 whole square. Instead of 8x minus x square, I write 16 minus x minus 4 whole square. Now doing substitution, first I have rewritten the form and then applying the substitution method. Now here, if a is, this is basically a form a square minus u square. If u is x minus 4 and a is 4, then taking the derivative, du is dx. The integral of 1 by under the radical a square minus u square is equals to sine inverse x by a according to the table. Here it is written. Integral of dx by under the radical a square minus x square is equals to sine inverse x by a, and I have told that sometimes we have to rewrite an integral to match it to a standard form in the table. So we have done the same thing here. So the integral is sine inverse u by a plus c, doing back substitution. So sine inverse x minus 4 by 4 plus c. So this is the integral. Now evaluate integral cos x sine 2x plus sine x cos 2x dx. Now what we'll do here, this is a formula of sine alpha plus beta. So sine x plus 2x, this is equals to sine 3x dx. Now doing substitution, let u equals to 3x. So the derivative is du equals to 3 dx. Take all the extra terms to the left. So we get 1 by 3 du equals to dx. So instead of dx, write 1 by 3 du, and this is sine u. Taking the integral of sine u, that is cos 3x. Taking the integral, I get minus cos u by u. Minus cos u, sorry. Minus cos u, so the integral is doing back substitution, I get minus 1 by 3 cos 3x plus c. Now this is another example of an indefinite integral, but this is an improper fraction. Why? Because the degree of the numerator is greater than the degree of the denominator. When this happens, divide it. After dividing it, I'm getting this expression, x minus 3 plus 6 by 3x plus 2. We know the integral of x, we know how to take the integral of 3, and we know the integral of 6 by 3x plus 2. So after integrating them, we get this answer plus a constant of integration, as this is an indefinite integral. So exercise 8.1 is basically a mixture of definite and indefinite integrals. Now here we can use any algebraic method or trigonometric identity and use the substitution method to reduce it to a standard form, or we can solve them. We can also solve them directly if we know the integrals. So starting exercise 8.1, question number 3, integral of secant x minus tan x whole square dx. So Applying a minus b whole square formula, this is secant square x minus 2 secant x tan x plus tan square x. Tan square x is equals to secant square x minus 1. Simplifying it, I get 2 secant square x minus 2 secant x tan x minus 1. As integral is a linear operator, we can apply it term by term. So 2 is a constant, taking 2 outside the integral. 2 integral secant square x dx, 2 integral secant x tan x dx, and integral 1 dx. Integral of secant square is tan x, integral of secant x tan x is secant x, integral of 1 is x plus the constant of integration. Question number 4. This is the definite integral because limits are given here. Domain is defined here. Let u is tan x. The derivative of du is secant square x dx. Secant square is basically 1 by cos square x dx. 1 by cos square x dx is part of the integrand. This means the substitution is perfect. Now applying now changing the limits, because as the variable is changed to u, the limits should also change. These are the limits for x and we need the limits for u. So when x is pi by 4, value of u is 1. When x is pi by 3, so tan pi by 3, after solving tan pi by 3, you get u equals to under the radical 3. So changing the limits, applying the substitution, 1 by u du, integrating it, I get ln of u, applying the limits. This is the answer. Here, in question number 5, integral 1 minus x by under the radical 1 minus x squared dx. We can write it as sum of two integrals. So 1 by under the radical 1 minus x squared dx minus x by under the radical 1 minus x squared dx. We know that this is a minus x squared dx. So the value of a is 1 here. So the integral is sine inverse x. Now moving towards the second part, we can do substitution here. Let u equals to 1 minus x squared. The derivative is du equals to minus 2x dx. X dx is part of the integrand. Moving all the extra terms to the left side, we get minus 1 by 2 du equals to x dx. Substituting the value here and integrating it, I get this expression. Question number 8 is also simple. Question number 12. This is an improper fraction, so dividing it, because the degree of the numerator is greater than the degree of the denominator. Doing long division here, I get this expression. Integrating 2x 3 and 2 by 2x plus 3. And this is the definite integral, so we have, if we are doing some substitution, that we have to change the limits as well. So changing the limits, we get this answer. Now question number 14, integral cosecant t sine 3t dt. Sine 3t can be written as sine 2t plus t, applying sine alpha plus beta formula. This is cos 2t sine t plus sine 2t cos t divided by sine t. Because of this cosecant t. Sine 2t can be written as 2 sine t cos t. Simplifying it, I get cos 2t plus 2 cos square t. Cos square t can be written as 1 plus cos 2t by 2. Simplifying it, I get this expression. Now we can solve this expression. We know the integrals of these functions. Integral of 1 is t. Integral of cos 2t is sine 2t plus some constant of integration. These are the simple questions. And these are not so difficult, so you can solve these questions and you can try to solve the remaining questions of exercise 8.1 and check your concepts.